Okay, I think I've made the necessary corrections. I had square roots of 3 where I meant 3 square root of 2 until I got down here and tried to justify the coordinates of this point. I just went on with my error. Okay, so here's my parameterization. I think I also had pi over 2, 3 pi over 2 here. It's pi over 4 and 3 pi over 4, which is what I said, not what I wrote. Okay, and it had it right here. Okay, so again, here's a function. Here's a parameterization of a surface which turns out to be a part of a sphere of radius 3. Here's a parameterization of a curve, of a boundary of the section. If you imagine the sphere centered at the origin with the z-axis coming out at you, what I'm parameterizing is this curve here that goes out to the extreme of the circular projection of the sphere and the circular rim of the sphere in the xy plane. We have a path that goes from the origin to here, along the rim of the sphere here, and back to the origin here. And then you imagine that this is maybe a cookie cutter, and we take this thing and we press it down through the sphere. So we cut out a section of the sphere, okay? And that section will be like a slice of orange. Cut the orange in half first, and then cut it here, and cut it here, and you got a section of the orange. Or grapefruit, whatever circular fruit you want to cut. Okay, here's a parameterization of this path. We'll see what this path is good for shortly. So I've already explained all this. The only part that wasn't right was I had square roots of 3, where I have 3 square roots of 2. Kind of unbelievable, but I did it. Okay, so there we have it. Now, the integral for Stokes Theorem of f dot dr, well, for this orange slice or whatever we wish, we cut the thing off at the xy plane, so this is going to be an open boundary, or a boundary of that surface. Okay, there are other boundaries that that surface could have, and we could integrate over those boundaries as well, but now here is boundary of that surface. This curve then is your curve C. C equals C1 plus C2 plus C3, so the integral over C is the integral of f dot dr over C is the integral of f dot dr over C1 plus the integral of f dot dr over C2 plus the integral of f dot dr over C3. And what's f dot dr? Well, dr for the curve for C1, C1 is parameterized by R1. So dr on the C1 curve is differential of this. So the dr dt is I plus j, so dr is I plus j times dt. Right there's your dr. So and let me go ahead and write that down. So if R on C1 is Ti plus Tj, then dr dt is I plus j, so the dr is I plus j dt, and right here it is. There's our f dot dr. F is yi plus zj plus xk. On this curve, y is your coefficient of j, that's t. Z is your coefficient of j, there's no z here, z is 0, because this curve is in the plane. So we get 0j. And then xk, x is the coefficient of I, so it's going to be tk. Okay, so part of the integral over our boundary is going to be this. The integral over C2, well, C2 is a part of the curve, corresponds to this parameterization. It's the arc of a circle of radius 1 between the pi over 2 and 3 pi over 4 and 3 pi over 4 angles, values of theta. So theta from pi over 4 to 3 pi over 4, 3 cosine theta plus 3 sine theta. Familiar parameterization. So when we integrate here, now our x is 3 cosine theta, our y is 3 sine theta. We're still in the xy plane, so z is 0. So that yi plus zj plus xk is 3 sine theta I plus 0j plus 3 cosine theta k. And that's multiplied by the dr we get here. Now we have a dr d theta equals what? Negative 3 sine theta I plus 3 cosine theta j. Well, there it is. And that's dr d theta, so the dr on this segment is just this times d theta. So, dot product of this and this. And then, similarly, on this last curve. And I won't read it all off too well, maybe. X is your negative 3 square root of 2 plus t, and y is your 3 square root of 2 minus t. Substituting those, we get an I and a k component that you read here, and 0 again for the j component. And your dr3 is what? If you take the derivative of this with respect to t, you get I, 1i, minus 1j. So it's I minus j, and then dt. So the dr here is I minus j dt. Okay. That's a boundary integral for this surface. Then you can verify that this is a boundary of this surface. Now the area, the surface integral, and I'm using ds instead of dA. I think I've got it all. Del cross f dot n ds. First of all, I'll just comment that the normal vector is just the vector xi plus yj plus zk divided by the magnitude of that vector. On the surface of this sphere, it's going to be xi plus yj plus zk divided by 3, because everywhere on the surface, the distance from the origin is 3. And that's the length of the vector xi plus yj plus zk. The vector xi plus yj plus zk, well, that's actually it. It's your r vector. And another way of saying it, well, we'll say it that way in a minute too. Okay. Your del cross f, there's your f. Your del cross f is this determinant. I don't have to read it to you. Comes out negative I minus j minus k. And that's all there is to it. So the del cross f is negative I minus j minus k. Your normal vector is your r vector divided by its magnitude, because your r is a vector from the origin out to the point of your sphere. Okay? Well, the r vector, I said, was xi plus yj plus zk, but we parameterized it as such, so we might as well just write it down as such. And magnitude of r, well, you can add up the squares of these coefficients, simplify it, and you're going to get 3. So there it is. This integrated over the surface is Am I leaving something out? Looks like I might be. How could I left that out? Well, having left that out, it doesn't work, but I'll insert it. Okay, so it's a surface integral. So we're integrating this dotted with this times your area increment, but your area increment has your magnitude of t theta cross t phi, because you're parameterizing in terms of theta and phi. So I'm going to need a little more room here. And I'm going to need a little more room here. Okay, there we have it. Then we're integrating theta first from pi over 4 to 3 pi over 4 according to our parameterization, phi from 0 to pi over 2, again according to our parameterization. Down here, again we need the t theta times cross t phi, but t theta cross t phi is just your r theta. T theta is your derivative of r with respect to theta. T phi is your derivative of r with respect to phi. When you do that magnitude of that cross product, you're going to have a 3 sine theta cosine theta d theta d phi. Okay, so that's going to complicate the integration a little bit. In any case, this integral is then going to have to be equal to this integral. I'm looking for my, hate it when that happens, last board here. Here we go. Yeah, these are going to be a little heavy. I think I can invert them. Actually, should have done this one first. So I'm going to stop and say that, well, there's your integral. Those are the two things that ought to be equal. Then we'll do this.